let's keep talking about data design. Okay, so say somebody asks you, that you want to capture information about your CD library, and well, you got all these CDs, and so you come up with some trivial representation of how you want to capture the data, and one obvious representation might be that, well, I'll need to capture data for every CD, right? The title of the CD, right? The year that it was released, the band, the genre. Right, so those are things that pop up in your mind right away. Well, obviously, I'll need to capture one record for every CD. That makes sense. And if you want to go a little more granular and want to see the songs that might be in a particular CD, you say, well, I'll need the records for those too, right? And so there'll be, for every song, I'll capture one record. So it'll be the track number, the song title, how long that is, right? And obviously, one CD is made up of a whole bunch of songs. So there's a one-to-many for that, right? I'll just have many CDs, and for every CD, there will be a whole bunch of tracks. So the obvious data representation that you might come up with is that here you have a CD and has a track. So you have a one-to-many. For one CD, you have multiple tracks, right? And that's just obvious to you when you do a first approximation of what your data model might be. And then you start entering the data. Right, and then you start realizing that maybe that wasn't a good idea, right? That some of the things that you might have wanted to capture, your data model doesn't support it. So even though something as trivial as coming up with the CDs and songs might not support things such as this. What if you encounter yourself with a CD that now can't be immediately cataloged as a genre. There is no genre because it actually might have multiple genres, right, in one CD. It doesn't fit perfectly in your data model, right? Because you would have thought, right, that as you might think, is that perhaps 80% of all CDs, typically a CD will only have one genre. It's either heavy metal, right, right, or whatever, right, and it has that one genre. But then you come up across these edge cases that don't fit nicely in your data model, right? And then you see the CD that has multiple genres. Well, how do I capture that? I only have one genre, right? So you have the brilliant idea that instead of just putting one genre in there, you do a comma-separated list of genres in there, right? It says, ooh, I'll just say genre 1, comma, genre 2, comma, genre 3 in that one thing, right? And you've just broken the first normalization, first normal form. Okay, that's one of the rules not to do that. Okay, and we'll see how to fix that. Then you come later on and says, okay, you start burning your own CD, but it has exactly the same songs, but in a different order. You burned it. You wanted to give a copy to your girlfriend, but you put it in a different order because you thought it might have been a better way to listen to the CD. And now you have this and you want to catalog it. It says, oh no, it has exactly the same title, the same exact release, the same band, has exactly the same songs, but the tracks are different, right? The ordering is different. So what do? Do I repeat the same song? I can't use a song that's already there because it's got a different order, right? So I'm going to have to replicate, right, the same exact content except for that one track number, right? It has the same title, same everything except that track number, and you enter that, and you've broken now the second normal form. Okay, that we'll see later on how to fix it. Right? So there's a whole bunch of things, right, that might look perfect at first, right? But depending on the questions you might have, the kind of questions you want to ask your query, now it breaks your normal form. This was assuming a particular set of requirements. Yes? If your requirements were that your assumption was that all your CDs are like this and all your tracks are like that and they're unique and whatnot, right? And if that's true, then that domain, that data set, that schema might be perfect, right? But as you start adding new requirements, you see that, oh wait, I can't do that, right? So you see how requirements actually drive your data, your analysis, right? Your choice of your data model, right? Even though you might be very knowledgeable about a particular domain, doesn't mean that requirements are not going to trip you over, right? They're not going to add a whole bunch of edge cases that your data model is not going to support. Yes? Right? So your requirements drive your data model. The data model is not going to be foolproof, right? You have to go back to the requirements. CDs with songs with various bands, right? Or where you might have a song that a whole bunch of bands, or maybe there was a collaboration, right? That one band member left the band, to join another band, right? And then came back. So for a moment they were in another genre, they came back, right? They produced their own records. So all these edge cases are not supported in your data model. So anyways, performance per band, it's just a mess. Okay, so the task of deciding what the data model is, that's data design. Okay, so anyway, so the idea would be that you should not start at the schema, right? At the class at the tables and fields and data types and things like that. That's not where the best place to start. The best place to start instead is to think of it in a graphical way, right? To first just draw a couple boxes and draw arrows between these boxes, right? And this just goes on paper, and paper holds everything, and it'll be easier to make modifications, right? It's a very common practice to first do the class diagram, maybe in one of these advanced tools, and then you push a button and it generates all the everything else. It generates your Java, it generates your C#, generates your SQL, generates everything for you, right? So and oftentimes you can just stay at the tool, right? And a lot of these tools are fairly advanced, so that they can do reverse engineering. They might even look at your schema and generate the class diagram for you, right? You can make some manipulations at a graphical way, and then you can push a button, and then send it back to the relational database, right? So the best place to start is at the graphical conceptual model, right? To make a class diagram that can hold these things, and then throw the requirements at your class data model and see if it holds it, right? And then make tweaks graphically, and then generate the needed relational schema. All right, so let's spend some time here in the class diagram. We see that there's cardinality. We talked about that already. One of the more common types of relationships is the one-to-many relationship. It's very common that one of these is associated with many of those, right? So if you give me one department, I can tell you many students in that department. If you give me a different department, there'll be a whole bunch of different set of students on this side, right? And that, or one-to-one, where one student might have one permit, right? And somebody might even argue, if there's a one-to-one, why not even capture this data inside of the student itself, right? And that's a valid argument, right? If there's only one of these, why not capture it? But ideally, we would like to capture a class diagram per concept, right? So the concept of the permit, the idea of a permit, right? And then all the attributes of that permit. Could we capture this here? Probably, right? It would. But is a student really associated to a license plate or a car? Right? Well, not necessarily, right? That seems to fall as part of a different concept, right? That a student might be associated to a permit, right? That has all these other attributes. You might have also an optional, where a student might have a permit or not, right? 0 or 1, right? So you capture all these ideas depending on the requirements, right? So a requirement would capture this, right? Whether it's one or the other. Here's a many-to-many, where you might, if you have a student that could graduate in, have multiple majors, right? That they have maybe a major and a minor, right? So they'll register in 2 different departments or 2 different colleges. So instead of being a one-to-many, then it would be a many-to-many. Again, driven by a requirement, the requirement. If you're not allowed to be enrolled in more than one department or more than one degree, then it would just be one to many, right? But if your college supports multiple degrees, then it's a many to many. Again, driven by the requirements. Relationship strengths. We say that on the we say that when you know exactly how many are participating in a relationship, we say that that's a strong relationship, or that the department is on the strong side of a relationship, right? So this is the relationship, right? And if you know exactly how many are participating, we say that that class is on the strong side. On the other side, you don't know how many. It might not even be there might not even be somebody on the other end, right? Because this star means 0 or more, right? So we call this the weak side of the association, right, of the relationship, right? The student is on the weak side of the association. So this is a weak to weak, right? This is a strong to strong. This is strong weak. And there might be multiple. So these are one of the more common ones: weak, strong, strong, weak, 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 strong, strong. So again, some jargon. All right. So it's again, class diagrams allow you to very visually be able to start seeing if your class diagram can answer certain questions, right? So from the class diagram, we can see immediately that we can answer certain questions. You know, if you give the students, I can see which sections they're enrolled for a particular course. I can determine all the courses. If you give me the students, you can see which professor taught what courses for a particular student, in what year, the size, the average size of the given course. So these are all questions that presumably we have drawn from the requirements, right? And from these requirements, we have drawn up the class diagram, right? Ideally, it's that way, right? You look at the requirements and then you design the class diagram that goes with those requirements. But you can't answer other things. Here's an example on how these would translate to a table, right? So for instance, these are just classes. So that in the student you might have multiple student, Alice, Bob, and Chuck, ABC. And there's a one-to-many between Alice and the enrollment. The enrollment, notice that the enrollment has a many-to-many, right, as captured here, many-to-many. That means that the student might be enrolled in multiple sections, but one section might have multiple students, not necessarily the same students, enroll in that section. So there's a many-to-many. So enrollment tells me, you know, that student is enrolled in that section, right? So it has references to both. So here's an example of that. We have an enrollment. This says that student 1, 2, 3, meaning Alice, right, is enrolled in 3 to 1, right, over here, which is Webb over there, right? It also tells me that the same student is also enrolled in 5, 6, 7, which is 4500, software engineering, right? It also tells me that these two students, Bob and Chuck, they're both enrolled in 5, 6, 7, which is 4500, right? So there's a reference going back and forth. And one of the cool things about a relational database is that allows you to navigate backwards and forwards, right? You can go from courses back to sections, back to enrollments, back to students, or the other way around, from students to enrollments to section down to courses, right? It allows you to navigate both ways. Not necessarily in object orientation, right? In Java, not necessarily, right? You can commonly in Java, typically you can only navigate one way, depending on how you implement it. But it's a more common way of implementing it to navigate only one way. You cannot navigate back. And we'll talk about some of these differences in representing things in object orientation or representing them in relational databases. So yeah, so here's just pointing out that these are references and how they can be used to navigate amongst the different records. Visually, these are some of the things that we cannot answer in our class diagram, right? We cannot answer if a student has changed majors. There's no history of what the majors were, right? We can only tell you the current major. We can't capture, for instance, that they were first in chemical engineering and then they moved over to civil engineering, right? There's no history of that. If this would have been a requirement, then our class diagram is no good, right? We would have to have some history for majors, right? or we can't, for instance, capture that a particular professor is advising any one student. Again, our class diagram doesn't support that. Again, if this were a requirement, we would have had to have a data model for that. Typically, we want to be able to convert and move around between these two worlds, the class diagram model and the relational model. And typically, they mapped fairly simple at a very shallow sense. They map easy, right? Classes map to tables, attributes to fields, relationships with foreign keys and primary keys, right? So what we'd like to be able to have is some algorithm, right? Some predictable mechanism that, given a class diagram, you can tell me what this relational data model is, or vice versa. Given a relational data model, give me a class diagram, right? At least at the shallow part, or the more common use cases, right? There are some edge cases like inheritance, overloading, and things like that that's just not captured in relational databases, right? So at least the more common. So let's look at transforming tables, going from relational database, going back to a class diagram. So let's see. So we have CDs, tracks, and lyrics, and the CDs have a primary key of a CD, the title, release year, band, and genre. You have tracks ID, CID, tracks, and whatnot. And then you have the lyrics. Lyrics, notice that lyrics have not only the text and the author, who authored the lyrics, but notice that this is a primary key, yes, but it's also a foreign key. Okay, notice that it's not only bold and underlined, but it's also italic. Right, so it's a foreign key as well. So its primary key is also a foreign key, right? Meaning that its value, right, happens to be the value of some primary key in some other table, right? So it's referring to records in the track table, right? And its value is taken from there. Right? So I cannot put here, just unique values. They have to exist in the track. See that? And that kind of enforces certain things. That you just can't have lyrics without a track existing. Makes sense. If there's no song, why would there be a lyric for that, right? So we're enforcing that, right? We're enforcing that there's a one-to-one there, right? So if the track goes, the lyric goes, right? So there's the dependency there. So let's look at that. So lyrics table holds lyrics and the author, but notice that the track ID, is a primary key and a foreign key. So each track can have at most one lyric, right? So notice that here we are enforcing that song can only have that lyric. That would make no sense to have a same song having multiple lyrics, right? That would make no sense, right? So here we're enforcing that. Each track, okay, so we're enforcing that each track only has one lyric. Many track records, okay, so some of the constraints, many track records have one CD, and one lyric has one track record. All right, so let's see, foreign keys, record, one CD record can have many tracks, right? Yes. One track record can have one or zero lyrics, okay. Let's see, what else? Foreign keys. Right, so the foreign keys tells you that that particular record is referencing some other record, right? So for instance, like a track references a CD, right? That you might have multiple tracks, right? Multiple tracks, right? Referencing one particular CD, right? You might have multiple track records referencing a particular CD, right? So this establishes the fact that one CD can have multiple records, so that's a one to a many relationship. Right, so that fact of foreign key tells us that if you have a foreign key and there's a primary key, typically you would capture that in a class diagram as a one-to-many, with the cardinality of 1 and star, right? Right. So here's just an example of multiple tracks referring to a particular CD, and that one lyric references exactly one track. Right. So that's just an example of what the data might look like, and here's how you would capture it in UML. Right, you have a CD class and one-to-many. Notice that in in a relational database, there's a field that captures the primary key. See that? In the relational database. In the relational, right? You capture the fact, right, that you have a primary key and you have a foreign key, right? But that's not actual data. Right? That's not actual data. That data is there only to capture the fact that there's a relationship between the two. Yeah, but that's not actually part of the song or the CD, right, or the lyrics. This data is only there to capture the fact that there's a relationship between the two. So what class diagrams do is that they don't even show those fields. Right? Notice that we're not showing here the field CID. Or here, we're not capturing the fact that there's a track ID, right? And we're not capturing the fact that there's a CID foreign key referencing back to the CD. You see that? We're not capturing those things. We only capture, in the class diagrams, we only capture the actual data. Yes? Right, so be careful, right? When you're doing your UML diagrams, do not capture the primary keys and foreign keys in the class diagram. Instead, those are captured graphically by the lines, right? They're captured by the cardinality. They're not captured by actual fields, all right? It would be redundant to say that this has a CID and a track ID, right? Or that this has a CID. It would be redundant. All right, so here's the algorithm. Yes?
I was going to say, you kind of lost me there a little bit. Sorry
What?
about that.
Yep.
So between CD and track, we don't want to say that, we don't want to say a CD is also a CD.
That the uniqueness, right, of this of an instance object of this, right, is already implied, right? An object has already the notion that is unique. It's an instance. There might be another instance that might have exactly the same values, just like there might be somebody else here also called Jose Annunziato. But even though we might have the same value, we are distinctly two different people, right? Two different instances of the human race. Yes. So in that sense, an object instance, right, has uniqueness already. I do not need a primary key to tell me that I'm unique, right? The fact that we have the same values doesn't make us the same person. Okay. Yes.
Professor, primary key is title. So if we want to keep title as primary key.
I'm sorry. Say again.
So
Ooh,
if
sorry.
we want to make title as a primary key,
Yes.
and now you're saying that we cannot store it, like we shouldn't store it, but losing title, like let's say.
Well, I'm not saying you shouldn't store it, right? I'm saying that the class diagram implies that you have all these other. I guess what I'm trying to say is that the relational database, it just happens to be one way to capture the data, and it has some syntax that forces you to add these additional arbitrary fields, right? Because there's no other way to capture the relationship. The only way to capture the relationship is the foreign key primary key. That in this other language called the UML language, right, we are already capturing the fact that they are related, right, through the use of these lines, right? That adding CID or TID or whatever, right, would be redundant because we already captured that idea in the line. Okay, that relational database just happened to be one way of capturing the data, just like we could have used CSV, right, a comma separated value or a tab delimited value, right, and then we would use some other way of capturing those relationships, maybe the name of the file or something. I don't know. Okay. Right. So here's the algorithm. The algorithm, given a table or given a set of tables, here's a generic algorithm that we could follow to give us the equivalent class diagram, right? So for each table, we can iterate over the tables, and so if you look at a particular table, table 1, you check to see if it has a foreign key, right? That if it has a foreign key pointing back to table 2. So you have two tables. Table 1 might have a foreign key back to table 2, right? If that's so, then you're going to create a relationship between two classes of the same name, right? So if you have two tables, right, T1 and T2, and T2 has a primary key that references a primary key here, so a primary key, right, where this is a foreign key and this is a primary key, right, then that converts to be a class of the same name, T1 and T2, and we create a relationship between the classes. So here's a relationship, right? The annotation next to T2 will be 1, and the annotation next to T1 will be 0, 1, if the foreign key is also a key. Right? If this foreign key is pointing to a primary key, right, then this would be 0 or 1. If it's not also a primary key, if this foreign key is not necessarily a primary key as well, then this is just a star. Right? So there's a one-to-many relationship between these two. All right? So these first two lines, in the algorithm allows us to convert a relational schema into an equivalent class diagram, and plus all the attributes, for each one of the fields, that are not foreign key or primary key, right? We're going to grab all those and we're just going to copy them as elements or attributes or properties of the classes. So this is a let's see, add attributes to each class. The attributes should include all fields of the table except for the foreign keys and any artificial keys, right? So don't capture those, since they already have been captured in the line. So let's take a look at this. If we apply this algorithm to this a little more involved class diagram, a relational model. Notice that we have a whole bunch of foreign keys. Right, we have primary keys over here, SID, DID, CID, whatnot. And then we have all these foreign keys, right? Student IDs and section IDs pointing to the students and the sections. This is pointing to a course. This is pointing to a department, right? So these are all referencing each other. So if we follow that, ideally you would come to this result, right? You would go and find that. So let's do it maybe between a student and enrollment. So between student and enrollment, if you look at student and you look at enrollment, we have that the enrollment here, the enrollment has a reference to a student, so it has a student ID, right? That is a foreign key over to the student table that has a student ID primary key. So this is a primary key. And there's a foreign key. Now this foreign key is not also a primary key, right? It's only a foreign key, right? So this is just referring to this. So according to the algorithm, you would create two class diagrams. One would be the enrollment class, and the other would be the student class. And on the side of the foreign key, there would be a star or a 0 to 1. Right, depending on whether this is also a primary key. It's not. It's only a foreign key. So it's a star and a 1 on the side of the primary key. Right? And that's basically this this part, right? This part, right? So one-to-many over here, right? And you can expect questions like this on an exam, right? I might give you a relational model, right? And I would ask you, give me the equivalent UML class diagram, applying so-and-so algorithm. Or vice versa. I'll give you the UML diagram, and you convert it into a relational model. All right? Okay? So practice using this easy example, right? Applying this algorithm. All right? So class diagrams is the way to go. To start first at the class diagram. A picture is worth 1,000 words. Typically, looking at a schema is just mind-numbing to try and follow all those foreign keys and primary keys everywhere, or looking at the create statements, right? It's just you would have to build your mental model, right, of what the relationships are. Right? Obviously, if it's a small database, perhaps you could do that. But any interesting database, right, will have many dozens of tables and relationships. So typically you would use one of these tools to look at the relational database. It applies algorithms such as this, and it generates a graphical representation, right? Then you can then manipulate change and whatnot, and then it can go back and tweak on it. So yeah, so first it's easier to go. You can go the other way around, right? If you have a class diagram, you can generate the relational schema, right? So if for every class you iterate over the classes, and for each class you generate a table, right. So and you're going to take the fields in the class, and they're going to become attributes for the table, so here we look at let's see, choose a primary key for each table. Okay, so we are generating a primary key for every table. All right, even if we don't need it, right? We'll generate an arbitrary primary key since we don't have it in the class diagram. We don't have those, right? So we're just going to generate a primary key. If there is a natural key, maybe you chose a natural key maybe as an email or a username, right? And you chose that's a natural primary key. Then use that, right? If that's useful. Otherwise, just generate an artificial key, right? And then look at the weak strong, where you have a one-to-many relationship. So add a foreign key on the weak side, and add a primary key on the strong side. Right, that's easy, right? So you take so it's basically going from here to here, right? Going backwards. Now this algorithm has its limitations. There's a whole bunch of things that it does not consider, right? There's a lot of other things that this algorithm cannot do. So the example, right? Take this sample class diagram and convert it back into the resulting schema, and make sure that you know how to go backwards and forwards between the two. All right. Once you have done the conversion from a class diagram to a relational schema, you might choose to tweak it a little bit, right? And realize that perhaps the resulting schema there might be some natural keys that you could use. For instance, you know that within the university the department name is unique. Right, you don't have two chemical departments. Okay, that the name of the department is unique, and you might choose to do away with some of the artificial primary keys, right, and just keep the natural keys. You might also rename some of your fields so that they better describe it, right? So since now we have changed the department a primary key to be a natural key, you can go back, and anybody who's referencing the department, instead of using the primary key, they can now use the name of the major name, right? Your chemical engineering or something, right? The name of the department would be useful, right? As opposed to just a artificial key. Also, let's see. Some of these. Foreign keys might be redundant, right? That you already have a uniqueness, right? That the student ID is already unique, right? If it's a one-to-one, right? If you know that this permit can only belong to one student, right? There's no point of keeping its identity, right? The identity can be the same identity as the student, right? Because one student gets one permit. So that permit cannot exist without the student, right? So it makes no sense to have for it to have its own identity. So we can remove the permit ID and then just use the student ID for that. Okay. So there's no need for the student ID to be its own foreign key. We can combine these two, and now this foreign key can also become its primary key. All right. Yes. Yeah, you would list it there, right? But there would be no distinguishing factor that it's a primary key. Right? There's no way that you would distinguish it. Oh, this is my primary key, right? It's just one more piece of data.
In that way, we need to keep that primary key in the class diagram, right?
Yes, right. But you would not declare it as a primary key, right? And then when you convert it into your relational representation, you would have to go through this cleanup and say, oh, wait, no, I already have this unique identifier. There's no need for an artificial primary key, right? Because I'm already using that as a primary key. Yes, right. Yeah, so don't capture things that are only used to create the relationship, basically. Yep. Because the relationship is already captured by the diagram itself. A couple other things here. You might realize that based on our requirements, somewhere in our requirements might have said that a student can only be enrolled in one section, that they cannot be enrolled in multiple times in the same section. And then that kind of realizes the fact that the combination of section and student has to be unique, right? You cannot allow, if these are just plain all foreign keys, one pointing to a student, one pointing to a section, all by itself, this would allow cases where the same student is enrolled in the same section twice. Right? There's nothing stopping us from doing that, right? And we would be breaking our own requirements, right, of uniqueness in the combination between student and section. So that kind of tells us that this needs to be unique, the combination of student and section. So we could combine this into a compound key, right? Put a curly bracket around it, and that needs to be unique. So this says that this is a primary key. So there's no need for an arbitrary, artificial primary key, right? Because already the combination of these two needs to be unique, right? And that would be now our primary key. Okay. Let's see, what else? Some more natural keys. The course, right? We would remove department ID now that we're using the title, the name of the department as our primary key. So now our foreign key is the name of the department. Also, the course names. We could decide that course numbers or titles are unique. Right? There's only one CS 5200. Right? There's only one CS some odd whatever. Right? So we could use the title as being unique, and use that use that natural key and replace it with title and CID. Same thing here, because we've made those changes in the course, we can go back and replace the course ID with just the title. All right. Right. There's some limitations in our algorithm. For instance, it can't deal with many-to-many. Right, or one-to-one. It can only deal with one-to-many, right, or many-to-one. But it can't deal with some of these other edge cases, and we'll work on those a little later. Some good practice of creating a good class diagram. First of all, you get some list of requirements. Those requirements usually will have lots of missing information, redundant information, contradictory information, right? Vague. It's very, very common. So typically, there's many rounds of meetings between you and the client to verify your understanding. So, but typically, you'll come up with a first preliminary class diagram, right? A naive class diagram, a first approximation, right? You'll list a preliminary list of nouns and verbs. And a first approximation what the class diagram might be. You'll start identifying some inadequate relationships, some redundant relationships. You'll apply the algorithms that we spoke about earlier, right? We will certainly look at the week-to-week and many-to-many. So many-to-manys and one-to-ones relationships. We'll identify attributes and decide whether it should be an attribute or a class. We'll go back and provide this class diagram back to our clients, and well, they probably won't know what to do with the class diagram, but we'll certainly ask questions, right, on the types of requirements, and that will affect your design, right? It'll be iterative. Unfortunately, we can't do that in class, so we'll rely on you making a first approximation and you defending your decisions on that first assignment. So 3 and 6 will have to happen multiple times. A lot of requirements analysis. So here's an example. University is composed of departments. Academic departments, such as mathematics and drama departments, are responsible for offering courses. Non-academic departments, such as admissions and dining hall departments, are responsible for other tasks that keep the university running. Irrelevant information, right, in our design. each student, and we're capturing all these nouns and all these verbs, right? The university has a graduation year, majors. Each year, the student who have not yet graduated enroll in 0 or more courses. A course may not be offered in a given year, but if it is offered, it can have 1 or more sections, each of which is taught by a professor. A student enrolls in a particular section of each desired course. So this might be, some of the narrative, right, for our database. A student is allowed to have 1 car. In order to park on campus, they need a permit, and so on and so forth. So to avoid misuse, a parking permit lists the license plate and model of the car. Some other requirement spec allows students to, so some of the things that the database should allow you to do: allow the students to declare and change majors, keep track of parking permits, allow departments to begin of the year to specify how many sections, allow current students to enroll, professors to assign grades. So some of those are the requirements. So here's a preliminary list of the nouns and the verbs, right? Fairly exhaustive. University, academic department, non-academic department, courses, students, years, grades, sections, professor. Lots of the verbs, right? Captured in some verb phrases that will give us an example. We'll capture some of the relationships between the nouns. The professors assigns grades, professors teaches a section offered in year. Students request permits, students is issued a permit. So a lot of these verb phrases that we capture from the narrative, a lot of them will be irrelevant. We don't care, okay? Also, we have to decide what the scope of the application is, right? How what is the granularity that we want to capture? For instance, if we're talking about cars, how granular should we be about cars? Do we care about the make and model, the year? Do we care about the color? Do we care whether it's a pickup truck or the SUV? Do we care about those things, right? It didn't seem to be the case, right? In our narrative, it looked like the license plate was enough and the car model was enough. And that's it, okay? So we have to decide what the scope of the database is, right? And how granular do we want to? For instance, university, is this? Are we doing this for one university or for a generic number of universities? Is it just one university? If it's just one university, typically there won't be a university class or university table, because that would imply that we are considering many instances of universities, but we're not. We're not considering multiple universities. We're only considering just this one university. Right, so there won't be a university class or university table. Maybe if this were the Department of Education and they have multiple universities, maybe in their database there might be a university class and a university table, because they're looking to capture data about multiple universities, right? But not us, right? That's not our scope. Other things that we don't care about, non-academic departments, that's irrelevant. Campus, that's irrelevant. Composed of, requests, those are all irrelevant. And we interview and discuss this with the stakeholders just to make sure. So this might be the beginnings of a class diagram, a naive class diagram. Like every noun seems to be worthy of being a class. So we have students and grades and departments and professors and sections and year, and we approximate our understanding of what this might be. All right, as we analyze this, right, hopefully at the end on the other side, we'll come up with the class diagram we started with. Okay? Ideally, you analyze this and you start removing some of these things or collapsing some of these together. Some of these are nouns and classes might actually become attributes of other classes, right? Or instead of it being a professor, for instance, one of the things that we noticed is that there didn't seem to be the need to capture a list of professors, right? There didn't seem to be the need for that. There was no requirement for capturing, any information other than maybe the name of the other professor, right? And maybe a class is too much; it's an overkill, right? Maybe just the name of the professor is enough to declare in the section, right? What the professor is, who taught that particular section. That's it. Maybe it's not enough. There's no need for even capturing the list of professors. So anyway, so some of these relationships might be Actually, how many? Let's take a short break, and then we'll continue with this. All right? We'll come back right after this.